In this video, we shall look at a few review problems associated with conservation of energy. Let's look at problem 1. A 10-gram object is fired vertically upward using a spring as shown. So that is the object. The spring is to be compressed 6 cm in order for the object to reach a height of 22 meters. So that's the height above the object's position on the compressed spring. Part A, find the change in the gravitational potential energy of the object as it gets to this 22 meter mark. So that's right there. Part B, find the change in elastic potential energy of the spring during its launch of the object. So let's do part A. Now, if we want to determine the change in gravitational potential energy, we know that to compute the change in gravitational potential energy, we need the final gravitational potential energy minus the initial gravitational potential energy. So let's look at the initial and the final positions of this object. So this is the initial position, and it gets up to that height, which is the final position. Now we can set the gravitational potential energy to be 0 at some point, and we shall choose the initial position to be that 0 joule mark. So that means that term goes away. So the change in gravitational potential energy is quite simply the gravitational potential energy at the final location. And that is simply given by mass times gravitational acceleration times the height from the 0 joule level. Now we know the mass. Mass is 10 grams. So let's change that into kg by dividing it by 1,000. Gravity is 9.81, that is the gravitational acceleration. And the height from the 0 joule level is 22 meters. And that will give you the answer, which is 2.16 joules. Now let's do part B. What is the change in the elastic potential energy of the spring? The change in elastic potential energy of that spring equals the final potential energy of the spring minus the initial potential energy of the spring. What is the final potential energy of the spring? The final potential energy of the spring is the energy of the spring when the spring is completely relaxed and the ball is already set into motion. So when the spring is completely relaxed, then there is no potential energy. So it is quite simply 0. That means the change in spring potential energy, or the elastic potential energy, is minus the potential energy of that spring at the initial state. Initial state is when the spring is compressed. Another thing to note is, according to the principle of conservation of energy, the elastic potential energy that the spring contains when it is at the compressed state, namely this number, is what provides the gravitational potential energy for the object when the object gets to the final state or the final mark. So we can say that the initial elastic potential energy of the spring in magnitude must be the same as the final gravitational potential energy of the object, which we have found above. Since we know what this is quite simply 2.16 joules, then we immediately get the change in elastic potential energy of the spring to be negative of that number. So now the answer is negative 2.16 joules. So that is the answer for part B. Problem 2. An object is moving with the speed of 40 meters per second. So that is this object right there. It's moving initially on a flat horizontal surface with a speed of 40 meters per second. The mass is 10,000 kilograms. Upon climbing the ramp, so there will come some time, the object will leave the flat surface and begin to climb. So upon climbing the ramp, it stops momentarily after traveling a distance d. And then, of course, because this surface here is frictionless, so there is no friction between the surface of the block and the surface of that ramp, it will, of course, eventually come down. So our task is to determine that distance d, namely the distance along the ramp as it stops momentarily. So we can use the conservation of energy principle to solve this. Let's choose that point to be the initial point and that point to be the final point. And we write down the sum of energies before and after, namely the energy the object has at the initial point must be the same as the energy it has at the final point. So the energy here is fully mechanical, so we need to determine the initial kinetic energy and the initial potential energy. So that is the initial gravitational potential energy of the object at the initial point and the initial kinetic energy at the same point, and the sum must be the same as the final gravitational potential energy plus the final kinetic energy of the object as it gets to the final point. We can take this level to be the 0 joule level for gravitational potential energy. Remember, we have the freedom to set the 0 joule anywhere we want. So that goes away. Another thing that goes away is the kinetic energy of the object at the final point. At that point, it comes to rest momentarily, so the speed is 0. So that means that is 0. So now we can equate the initial kinetic energy to the final gravitational potential energy. Initial kinetic energy is half times mass, which we know to be 10,000 kg. Speed is 40, that is the speed at that initial point. Don't forget to square it, because kinetic energy is given by half mass square of speed, equals the gravitational potential energy at the final point is again mass, 10,000 kg, gravitational acceleration g, times the vertical height h. So what is that height h? Now we can express height h in terms of d and angle 20 degrees. So this is a right angle triangle, so that means your h is d sine 20 degrees. Remember, this is h, because the expression for gravitational potential energy is mgh. The mass goes away. We know everything except this d, and we can solve for that d. And it will give you 238 meters as an answer for d. Problem 3. At t equals to 0 seconds, a 2 kg object is thrown from a certain altitude with an initial velocity given by that expression. If the object is moving solely under the influence of Earth's gravity, find the change in the gravitational potential energy between t equals to 0 seconds and t equals to 5 seconds. The first thing to realize is the motion of this object is in the gravitational field, so the acceleration is minus g. It is a constant, so we can apply kinematics as well as conservation of energy to solve this problem. So according to kinematics, the speed or the velocity at any time t is given by the initial speed plus, or the initial velocity that is, plus the acceleration times time. And this acceleration vector is a constant. So let's substitute the expression for u, which we know is 15 I hat plus 20 j hat meter per second. Acceleration is minus g because the acceleration is downward. So it's minus g j hat times time. So what that means is the velocity vector is quite simply 15 I hat plus 20 minus gt j hat. Having found this expression, we can calculate its kinetic energy at any time t. So let's compare the energies at these two different times. At t equals to 0, its potential energy is U0, kinetic energy is K0. And at t equals to 5, the potential energy, the gravitational potential energy that is U5, and kinetic energy is K5. Conservation of energy says they must be the same. So the change in gravitational potential energy is the gravitational potential energy at t equals to 5 minus the gravitational potential energy at t equals to 0. And that is quite simply the kinetic energy at t equals to 0 minus the kinetic energy at t equals to 5. So what is kinetic energy at t equals to 0? It's half times the mass is 2 kg, and the speed squared is 15 squared plus 20 squared. That is computing the magnitude of that vector and squaring it. So this expression is u squared. What about kinetic energy at t equals to 5 seconds? It's half times 2. And we need to figure out the speed at t equals to 5 and square that. Note that the velocity at t equals to 5 can be readily found from that expression. It's 15I hat plus 20 minus 5g j hat. And that is, so that means this term right there is 15 squared plus minus 29 squared. So that means we have a numerical value for K0 and numerical value for K5. And according to this equation, by subtracting K5 from K0, we get minus 441 joules. And that is the answer. The last problem. The ball shown in figure is attached to a 1 meter string. Upon releasing from rest, that means from here, from the horizontal position, that is, it travels along a dotted path like that. Now, after this string hit the pin, denoted in red here, the ball will continue to travel in a smaller circular trajectory until the highest point is reached thereafter. That is to say, after this point, it will move in a smaller trajectory, something like that. Find the ball's speed at the lowest point, which means here, and also the ball's speed at the highest point after the string catches on the pin, meaning there. So for part A, I'm going to set this as the initial position, that is the final position, and I'm going to take the potential energy to be 0 there. So conservation of energy will give you kinetic energy plus gravitational potential energy at the initial position equals kinetic energy at the final position plus gravitational potential energy at the final position. The object is rest here, so that's 0. And this is the 0 joule level for potential energy, so that's 0. The initial gravitational potential energy is the mass of that ball times gravitational acceleration times this entire height, which we know to be 1 meter. The kinetic energy at the final point is half times mass times the final speed squared. So this is the speed at that point which we are interested in. Mass cancels and you can determine V sub f. And the calculation gives 4.43 meter per second for V sub f. So that's the answer for part A. Part B, what is the ball speed at the highest point after the string catches on the pin? So it's going to move like that, let's say. So what is the speed there? So for part B, this is going to be the initial point and that's going to be the final point. So note that from this conservation of energy equation, at this point, the potential energy is 0, so that's going to go away. Kinetic energy here can be calculated. It's half times mass times the speed there, which is that. It's 4.43 squared equals the kinetic energy there is half times mass times the speed squared. So this is the speed there, which is what we want to determine. Now U sub f, potential energy there, so plus mg, this entire height. Note that this is 70 cm, so this must be 30 cm, so 30 cm times 2 is 60 cm, so 0.6 meter. Mass cancels, and you can determine V sub f, which will turn out to be 2.8 meter per second. And that solves the problem. Thanks for watching.